Can you guys see this?
Yep.
All right, sweet. Yeah, just like when do you guys want me to start?
Oh, you can go ahead right now. Kind of give a little spiel as to, kind of who you are. But aside from that, you can, you're in full control. And if you have any other questions, you can like let Jen and I know.
Okay. Yeah. So yeah, what I was thinking of doing was just because I don't know if you guys are waiting on a certain amount of people before I start talking, but it's sort of I'm trying to make it informal, but there's like some formal notation in it, but I'm trying to make it as like trying to make it like 45 minutes, but I don't know if I would be able to do it for 45. So if you guys have questions, any point, just like interrupt me or just like ask in the chat. I'll try to just answer them. Okay. Yeah. So just a quick intro. Oh, another thing. Are you guys recording this or?
Yeah, I'm recording this. Yeah.
Okay, sweet. Yeah, so I can just get started. Yeah, so hey everyone. I'm Qasim. I'm a junior studying computer engineering and machine learning. And I want to talk about a really exciting and interesting part of ML that is recently has gotten a lot of hype to it, but is still at its infancy when compared to other ML techniques. And so this talk, as mentioned, is going to be try to make it as high level as possible, but I'll put in some formal definitions here and there. Yeah, so as we all know, so I'm assuming there's some familiarity within deep learning and neural networks within the audience. So in general, I think, yeah, ever since 2013, when the deep learning curve just really blew up, we've seen that deep learning models have outperformed any other ML or traditional statistical models. And they've also outperformed human level performance in areas from image recognition to speech recognition to reinforcement learning tasks, such as playing games like chess, Go, to more complex competitive games such as Dota. And recently, AlphaFold, the protein synthesis algorithm that DeepMind had generated, sort of outperformed or broke some 30-year-old record. And so there's a lot of progress being made through leveraging deep learning algorithms. And so when we look at it from a larger perspective or from a different perspective in terms of if you were to plot it in terms of the amount of data and how these models perform, you can sort of tell that the more data that you have and the deeper the network, that is, the more hidden layers there are and the more connections between multiple nodes, the higher the performance. So we look at traditional ML, such as linear regression or linear classifiers. An example of that would be support vector machines, right? You use those techniques and you see how those models compare to more, I guess, yeah, so anti-rule based classification techniques, such as you have CNNs and RNNs and those kind of techniques. And you can tell that the number of parameters in a convolutional neural network out competes or out is just almost is bigger than the number of parameters used in a kernel machine or an SVM by a huge order of magnitude. And this leads to a really interesting idea that how much of the model or the parameters is really dependent upon the training data. And the idea is that the entire training data is sort of, or the entire model is trained on some data, and that data is basically a representation of the model itself. So if I feed in, let's say I have an image processing or image recognition task, and I'm trying to recognize between dogs and cats. But if I train the model on dogs and cats, but if the output test image is fish and cats or fish and pandas, the model will perform poorly because the true distribution of the test image or the test set was not really met within the overall training distribution. And this sort of gives you the ability to think that the underlying training data plays a huge role when it comes to building these ML models. And for those of you that took or have more formal experience with machine learning, you can sort of identify the similarities between a neural network, which essentially operates on the idea of gradient descent, where it's sort of a convex, kind of like a convex optimization problem where you're trying to minimize the gradient, or in the case of gradient descent, you're trying to maximize the gradient, versus that of a support vector machine, or more generally, a kernel machine, where you're trying to build a classifier, a linear classifier that can, with the highest margin between two or multiple classes. And the idea was proposed by, it's not really a new idea, but it's kind of interesting to think about neural networks being related with the classical techniques and how you can connect them together. And the idea, one of the implications of this idea is that when you're building your neural network model, let's say on TensorFlow or PyTorch, the essential data set basically gives you some form of illusion in terms of how useful or how accurate your final model would be. So if you trained it on a really poor data set, your final results would be really terrible. And as they say, garbage in, garbage out. So if I were to train it on a data with, let's say, cats and images, but the test set is on completely different distribution, the model would perform really poorly. And that sort of builds up to some of the common problems with deep learning. The first is the more complex the model, which is the more number of parameters and the more connections between layers, the harder it is to really understand what's going on. And at the same time, the performance goes up because the more complex, the more nuanced representation the model can really learn. You take a look at logistic regression, it's sort of very simple and highly interpretable, but the problem with logistic regression is that it cannot capture higher order interactions between data points as compared to a neural network, which can sort of take arbitrary data set and sort of understand some form of basic representation between it. And this sort of leads to the key problem, which I'll sort of talk about in this talk, which is the lack of interpretability in deep learning models. And there's this really good paper from Ian Goodfellow that was published in iClear just a couple of years ago, where, and so before that, there's this idea of combining, really to understand the robustness of neural networks by combining cybersecurity with deep learning. And this whole junction is known as adversarial ML, where you try to attack neural network models with some form of defense or attack. And the idea is, let's say you have an image, in this case, a panda, and the model predicts that, so it's already a pre-trained model, and the model now predicts it's a panda with around 60% confidence. So it's mid-tier confidence. And that could be a softmax output, depending upon the number of classes. So a common data set that is often used is the ImageNet, and you can really tell the confidence based on the number of classes. And let's say that you add in some noise to the original image, which is panda, weighted by some constant epsilon, in this case 0.007, and you sort of get the output as another image. And visually, if you look at the graph or the picture to the right, both pandas look visually indistinguishable. You can't really identify with the naked eye the difference between them. And the noise function that's added in is a very specific noise function. It's not an arbitrary function, but to the human eye, you can't really tell if it's a specially crafted noise function or a random Gaussian distributed noise function. And when the model now predicts the output image or the image embedded with some noise, it's two things happen. First, it predicts, it no longer predicts a panda, but it now predicts a gibbon. So it has basically changed its entire prediction. But I think the more interesting thing is it predicts a gibbon with almost 100% certainty. Previously, it predicted panda with like 60% confidence. Now it predicts the wrong class with almost a guarantee that that is the true class or the true label. And the reason for this is that the underlying data set plays a key role in how these ML models are trained. When you have a lot of labels or a lot of data set or a lot of points from the same class, but you add in poisoned or carefully crafted images or data set or data points within a cluster of clean or original or good data points, you can essentially shift the decision boundary towards one or the other end. And when you do so, the neural network no longer accurately predicts between multiple classes or between different outputs. And so it really does matter how you're crafting or how you're using your data sets. And that's a huge problem because this could be applicable to the self-driving industry, where you're trying to classify if you should stop or not if you're at a stop sign. And you could basically convert a stop sign into something that's, if it's a red light, you can convert it into a green light, and that would basically be really have the opposite effects to what you want it to happen. And this is a really important problem to address in the ML community before we start trusting them. And this is sort of the reason why it's so hard to deploy ML systems in healthcare and other financial industries where you can't really understand what they're doing. So now that we talked about, or there was a little bit of, I guess, more formally, more informally, the need for building trust-based systems or explaining why a model made the decision it did. I guess, yeah, so that leads to the idea, the main part of the talk, which is why did a machine learning model make the decision it did? And more specifically, can you make an ML model explain its decision? And if you can build better ML models. You can understand the distribution shifts, which is trying to understand how the training data differs from the testing data, and build what is known as label mismatch systems, which is where you can train ML models to build better classification systems, such as clustering algorithms. So you could improve unsupervised learning tasks by just understanding how they work. And they work in two different areas. The first, so the reason it's known as Blackbox is just because as of now, it's still, you can debate about it, but it's still kind of just shared across the ML community that it's very hard to understand at least for more complex models, why the model made the prediction it did. And so the two areas where you can just naturally understand what the model's doing is in the training and the inference phase. So at the training phase, you're trying to understand the effects that your training data has to the model. in the inference or the after you've trained the model, you're trying to understand the effects of the individual neurons and layers when predicting a certain image or a certain label. And the key difference lies in the training set having it treats the model as a function of training data, while as the inference treats the model as being fixed and I guess more pre-trained in the sense that you don't really train a model when it comes to testing. It's assumed that you already have an existing model. And two areas or two techniques where two types or two different domains where it's used are in the training area, the main techniques that are being used are influence functions and Shapley value, which are borrowed from the areas in game theory and statistics, where you're trying to understand the contributions of individual data points to the final prediction or final model. And for the inference, you have more traditional, more ML-related techniques such as occlusions and gradient-based attributions, which is trying to understand the quantification or trying to quantify the impact per neuron or per pixel in the final trained model. So the first technique is attributions. Essentially, what attributions tells you is for a given observation and an output, can you give an importance score to every single part of the network that contributed to that output? And ideally, all the nodes would have to contribute some way, regardless of the quantity to that output. So in the case you have a 3-layer fully connected neural network, you're trying to understand the output or the contributions every single node had in those 3 layers. And depending upon which layer or which nodes have more higher contributions, you can build better or have more understanding or more unique understanding of how these models or the essential distribution of the contributions with respect to the training data. So as mentioned, the training data is fixed, but when you have understanding of the nodes that are being used or the most important nodes and the least important nodes, you can do normal feature selection, such as PCA or other dimensionality reduction techniques. And this could be used or applicable as another feature reduction technique in your toolbox. And there are multiple techniques within the attribution framework where you're trying to understand the quantification of a single neuron to an entire layer. The most frequent ones are the occlusion and the most intuitive is the occlusion technique where you're taking in a pixel and you're trying to predict the output given that pixel. And so let's say you have an image of a snake, but instead of to understand the how the model performs or predicts the prediction changes, what you do is instead of having the entire image of, let's say, m by n pixels, you take just the first pixel and make a prediction based on that. And so naturally, that prediction would be the least prediction or the smallest value possible because you can't really identify a snake with just one pixel. So what you do is you try to increase the level of pixels that you use. So now you go from 1 pixel to 2, and you sort of build this sort of matrix where it's essentially a square or a rectangular matrix where you're trying to increase the number of pixels you're using and trying to check the difference in the previous predictions and the current prediction. And from there, you can build what is known as a saliency map or a heat map where you're trying to understand the essentially the contributions each individual pixel has to the final output. And from this figure, you can see that when you have 15 pixels or 15 by 15 pixels at the middle right, the image sort of has the highest prediction highest positive prediction towards that label. And the pixels that are highlighted as red contribute positively towards that prediction, while the pixels that are highlighted as blue suppress that prediction. And when you look at occlusion 1, 5, or 10, you notice that a lot of areas are highlighted as red. And the reason for that is because you have condensed the amount of pixels that you're using, a lot of points are sort of meaningless to the final prediction. So a lot of it is just pure randomness and just uninteresting results. But when you increase a domain by a specific and a significant amount, you can really identify the most shaded or the most heated areas. And that sort of tells you at a higher level the most useful pixels in that prediction. And the obvious takeaway from this is, or one of the drawbacks why this technique isn't that popular, is because it's super prohibitive in terms of how much you have to compute per image. You're basically predicting, inferring for every single pixel, and you keep on increasing it. And so this becomes computationally very expensive, and it's on the order of polynomial time. And besides the fact that it's super exhaustive to train or to build, another problem that it has is what is known as a network saturation problem. If you look at the image to the top right, it's a very simple neural network with just one hidden layer, 2 inputs and 1 output, where the output is just 1 minus the output from the hidden layer. And if we have multiple inputs, say I1 and I2 with arbitrary values, the hidden function is just the max of 0 and 1 minus the summation of those 2 inputs. And if we were to use the occlusion function to try to understand the relationship between the inputs and the final prediction, what we would do is we would change I1 and see the changes in Y. We would change I2 and see the changes in Y. But let's say that I1 is 0, or I1 is a very negative value, and you were to change it to a smaller negative value. The output would still be equal to 1, or the output would still be equal to 1 because the hidden layer is just the max of 0 and something negative. So regardless of what I change my I1 and I2, if it's very low, the output is still going to be the same. So what it tells you is that no matter what I do with my inputs, the output is still the same. And so therefore, those inputs don't really matter. But in this case, that's incorrect because those are the only 2 inputs and they must lead to something. And this is known as the saturation problem, which is not just used in ML, but in other areas in statistics. So a really interesting paper from Google, I think it was published a couple of years ago, talks about the idea for integrated gradients. And so this is the last paper that I'll talk about before moving to the next interesting topic. But essentially, what you noticed was from the occlusions that you can build something, you can have some higher dimension or higher understanding of certain models or certain data sets if you have enough computational power or if the model is diverse enough. And the idea that sort of naturally comes about is, what if you were to take the output and you multiplied it by the input or the features? What if you took the weights when classifying a certain image and you multiplied it with the inputs? Could that lead to some interesting results? And so it turns out that it does lead to interesting attributions, but the problem with that is that the more complex a model, the less likely that you are to get anything meaningful. And another proposed idea was to use this notion of gradient times input, where you take the gradient of the output, which is with respect to the input, and you multiply that by the input. So it's essentially the partial derivative with respect to the inputs, and you multiply that by the input. And let's say if you have a linear classifier and you do that, you can have a very fine differentiation between classes that are below the decision boundary and classes that are above the decision boundary. And when you sort of take that technique and you apply it to the image that you see in the center, where you have a fireboat, and you take the gradient and you multiply it by the features, you notice this white graph with just not really interesting results. And the reason for that is the more complex the model and the more nonlinear the model, the harder it is to really have some sense of what's going on. And the paper from Google, which was about taking the concept of multiplying the gradient with the inputs, what they proposed was, why not, instead of just the gradient times the input, we first scale the image to a black canvas and see the difference between the predictions and that output, and sort of scale it up until the image goes from a black canvas to has less opacity, until it has zero opacity, which is the clean input image. And what you see in this figure is when you have a black image, whatever prediction you make, the output is essentially the smallest possible value, right? If I have a black image and I'm trying to predict if it's a fireboat, you can't really predict anything at all because you don't have any meaningful insights or meaningful pixels. And so now if I brighten it up, or if I get rid of some of the opacity, you can see the prediction go up until a certain point when I have, say, 30% intensity, that you can see that the prediction goes about to 100%, which means the model is predicting that as a fireboat by full certainty. And at that point, you notice something really interesting. If you look at the gradients, which is the black images on the second row, the second image tells you that, gives you a really good or really clear understanding of the gradients, and it shows you the form of the gradients which are responsible. So the entire image are gradients, but the white pixels essentially are the positive values, and the black ones are negative or correspond to zero values. And the form or the pattern that they represent is the exact pattern for what you would notice a fireboat to look like. And this is really interesting because now that you know now that you know how the gradients of an image perform, you can really take that concept and build it up to other classes and try to see how different images of different classes have their gradients as. And from there, you can understand what features for different images have the most useful information when predicting those images. So in the case of fireboat, it really cares about the structure of a boat. And unlike a regular boat, it really cares about having these sprouts that sort of go up or shoot from the top. And that's very interesting. That could be used in a lot of tasks to explain why a model made the prediction it did. Yeah, so if you guys have any questions, just stop me or put in the chat. So the other, before we talked about this notion of having this fixed model and trying to understand the contributions of every single neuron. But initially when I talked about how the entire how the entire model is based on this function of a training data set, why not try to understand the importance of an individual data point when making the prediction? So the key questions that one of these papers tries to answer is, why did the model make the prediction it did? And we sort of talked about that previously. But on, two more important questions are, which training points were responsible for this prediction? Say we have a data set of cats and dogs. Let's say I give you a test data set and it's a picture of my cat. Can you explain, or can you find the most common or the most similar images, or the most important images that led to that prediction? Now, for those of you that are already familiar with ML, you would probably think of it as, why not just use KNN or some nearest neighbor approach, where you're trying to find the similarity between the test point and the data set. Turns out it's actually not possible or not feasible, or it's very hard to get a really useful or insightful information because these nearest neighbor approaches, they only sort of give you clustering-based information on superficial representation. And I'll talk more about that in a bit. And another question that the paper tries to answer, which I think is more important, is if we were to change a prediction in the original training data set, how would the model perform? And essentially, if we were to make one of the data points to have more significance than the other ones, how does the essential model perform? So I won't go into the details of the paper, but if you think about it from the perspective of how a human would try to perform this task, let's say that I have a cat data set and a dog data set, and I'm combining them, and I'm trying to understand the relationship between the two classes. And let's say there's this model where I push this button and it gives me some prediction from 0 to 1 if it's a cat or a dog. And so if I were to tell you what training points were the most, what if I were to tell you to pick one of the training points, let's say X sub K, and make multiple copies of it, could you sort of tell me the output or the final prediction based on those additional copies? And the answer is yes. You would retrain or rerun the model and try to see the changes from the original data set and the current data set, which has additional copies of one of the same images. And from there, you can really get that difference and try to understand if that individual cat image had more significance to the final prediction than previously. And if you see that the prediction goes up when you have multiple copies of the same image, you now know that the original image that you first selected has more significance. But that's not universally true. Not all images have the same amount of importance when making a prediction. And if the prediction goes down when you have multiple copies of the same image, then you have the opposite effects. And so that image itself was not useful at all. So just like we talked about in occlusions, where you're trying to do this recursively, this whole process is very computationally exhaustive. You're running the empirical risk minimization problem for every single image multiple times, and you're retraining the model. And this becomes a polynomial time problem. And to solve this, there's this idea which was borrowed from statistics and known as influence functions, which was sort of published, I believe, in 1980s. So it's a fairly old idea, but the idea is to, given a model, can you tell me what how important each individual point in that model is? So we're no longer talking about the weights, but we're talking about the data points that are used to train that model. And the way it's sort of done as a high level is by taking the approximation for what is known as the Hessian vector product. And that is sort of a second order optimization problem to avoid calculating the Hessian. And for those of you familiar with the Hessian, it's essentially the second order derivative of a function. And the problem with just using the inverse Hessian is that it's super computationally inefficient when you're doing it for multiple times. And the paper really comes up with an interesting approximation to avoid calculating it. And if you're interested, you can read the proof of the paper. Yeah, and so that's the idea behind this, is to take in a training point and perturb it or change it or upweight it by some constant and try to see the relationship or the effects that you had when you changed it or made it more important or less important than the original data set. And the results are really interesting. So as mentioned before, we talked about how why not just use a nearest neighbor or a clustering algorithm to really understand the difference between multiple features or multiple classes. What ends up happening is in the image that you see, you have multiple classes, and let's say you're trying to differentiate between or predict the difference or classify between a dog and a fish. And when we use a support vector machine, what we notice is that, let's say you have, you train a model using an SVM and you train another model using a deep net. And Inception is a very famous pre-trained model, which I believe was made by Google, but if someone knows who truly made it, just like put in the chat because I don't remember. But the idea is to have one model where it takes in a nearest neighbor approach and the other model, which is done using a deep net, and you try to predict the image from the test set. And let's say the test set has an image of a fish, and now let's say we use the techniques that I showed earlier about influence functions, and you try to see what points from the SVM led to that image being predicted as a fish. So in the case for an SVM, you can see that you have two images that are very similar to what a fish would look, or the features of a fish in terms of the color, but they're not really fish themselves. They just have very similar superficial features. But in the case that you train it on a deep net, you can see that it has gathered very much more deep representation or latent representation between what a fish should look like. And this is really important as the difference between why we can't just use a nearest neighbor approach, because the nearest neighbor from this only measures really superficial differences between functions or between different data points. And so for those who are familiar with convolutional neural networks, the idea of going from a fully connected layer to ConvNet is so that you can have more higher, or just have higher or deeper representations of the images in a 3D or 2D, to go from 1D to multiple dimensions. And so that's the similar, and we can prove that by just using influence functions and see how those things work. So as mentioned earlier, they can be used in a lot of different areas, such as understanding the behavior of a model and trying to understand why a model made the prediction it did. And it could also be used in defense attacks. So I'm pretty sure some of you are familiar with GANs and this website called This Person Does Not Exist, where every time you load this page, it gives you a new image of this person. And all those people are generated by this deep net. And while GANs are really great at generating new images or new points, they're also the underlying idea is to have a defender and an attacker, where you're trying to play between the two agents and try to build more or build harder models to defend against and harder models to attack against. And using the idea of influence, you can really go in that direction and trying to build models that are really hard to fight against, and at the same time, models that are really easy to break just by finding out the pixels that are the most vulnerable. And as mentioned, another topic of interest is the idea of domain mismatch. So let's say that I have, going back to the same examples before, I have the training data set on cats and dogs, but the test data set is the distribution across fish and pandas. So now the domain or the distribution from the training set and the test set are completely different. How can the model still have reasonable prediction or reasonable accuracy for those cases? And this area is very useful in the domains of reinforcement learning. And if any of you are familiar with reinforcement learning, one of the challenging problems with RL is that they're very hard to generalize. You need to have millions or thousands and millions of episodes to come about any general policy. And the beauty in reinforcement learning is that it's the truest form of learning when compared with any other ML technique. The main problem, besides having so many data points to learn from, is that there still aren't many pre-trained RL models, because in the case of humans, even though we do learn from you could sort of take relationships or have similarities between how the human learns versus how an RL agent learns, humans have a lot of pre-trained models that have just been installed in them. But in the case of an RL agent, everything's learned from scratch, so it needs more data. And that's a huge challenge, because if we go from one task to, let's say, playing chess, to now another task, such as finding out the efficient power supply in an energy grid, the two tasks are very different, but there are a lot of similarities in terms of the strategies that could be used to maximize any of the two tasks. And instead of retraining the entire model again and again, having some shared parameters could sort of give about new breakthrough algorithms in the areas of RL. And so, yeah, just to sort of conclude on the topic, my current research is on the idea. So one of the problems that influence functions and attribution functions try to solve is, given some data, can you identify the importance of either the individual neurons or the importance of an individual data point? But the problem still is that in reality, it's actually, a data set is not completely independent. It's when you have a data set of cats and dogs, multiple dogs that are of the same breed have more similar features than dogs that are of different breeds, even though they're the same species. And so this leads to a very structure-based approach where you can have higher order interaction between multiple data points. So you could have interaction between multiple ethnicities, even though they're of let's say, the same gender or the same people. And when you have this understanding, it's really hard to figure out the importance of that individual person or that individual breed of dog, and instead go from there to having a structural understanding of a cluster of data points based on some high order similarities. And that's sort of what our research is based on, is instead of just finding importance in one data point, why not try to find the importance in a structure of data points where you have now a graphical model and a directed or an undirected acyclic graphical model, and trying to understand the predictions and referencing the importance between that entire structure as compared to just one individual data point. Yeah, and so I think, yeah, that's about it. If any of you are still interested in reading any of the following papers that I talked about, you can go to any of the links, and it was I think, yeah, it was also shared on the Discord. So yeah, that's about it. Thanks.